Okay, start recording. Okay, so we'll continue with the analysis. So we started with the particle content of the MSSN. Is essentially that we take only different every matter field of the standard model. So Q, which is left-handed, UL, DL. We make it into a superfield, chiral superfield. So UL tilde, DL, DL. So this is one chiral superfield. This is another chiral superfield. So for every matter superfield, a matter field, we'll have a chiral superfield. Okay. And then for every vector field, so essentially photon, Z mu, W mu, we add a vector superfield. Okay. And then we needed to add two Higgs bosons, Hu and Hd, for two reasons. One is to give masses to both up and down type quarks masses, and secondly to cancel anomalies. Anomaly cancellation is coming because we are adding new fermions in the Higgs boson. These are also chiral superfields, but then these are new kinds of fermions in the standard model because they are charged under electroweak symmetry, electroweak gauge symmetry. Because you are having new fermions which are chiral, so you're adding new chiral fermions. They contribute to the chiral anomaly, so you need to cancel that. So you need to add opposite chiralities, opposite charges, chiral fermions, which cancel the anomalies. Okay, so this is about the particle content, and then we started writing K, which is sum over all the fields, I, sum phi I dagger, e power gv phi I. This we saw the expansion in the last class essentially. And then we also have the W. So the W has two parts. One is the just recall part, which we write the QI, UI CH2 plus YD QI DJ CH1 plus YE Li EJC H1 plus mu H1 H2. And the second part plus plus bunch of terms which violate lepton and baryon number. So this is let me write lambda double prime IJK UIC DJC DJC plus lambda I Li IJK QJ DKC lambda IJK Li LJ EKC plus epsilon ILI H2. So these are your terms which violate lepton number and baryon number. So we were discussing these terms, and I said that they have strong phenomenological implications, like they lead to very fast proton decay, So they should be completely suppressed. Okay, so that means that you have lambda prime, lambda double prime product should be less than or equal to 10 power minus 24. So orders of magnitude smaller than 1. So they should be very close to 0 essentially. So the best way is to somehow avoid these terms completely and set them to 0. Okay. So to do that, I introduced a new simple symmetry called R parity. R parity is defined on the component fields. Can define it on the component field such that Rp is equal to -1, 3, B minus L plus 2 S. S is the spin. B is the baryon number. L is the lepton number. See, like I think last time we discussed why R parity violating terms are allowed, meaning why lepton and baryon number violating terms are allowed in supersymmetric theories. When you write SU2 cross SU3 cross U1 Lagrangians compared to say standard model. So why they are allowed in supersymmetric theories but not allowed in standard model? The reason is the supersymmetric theories do not distinguish between the spin of the particles. They don't distinguish between the spin of so they cannot distinguish whether the Higgs is a scalar or a lepton. So and the lepton, because leptons and Higgs have the same quantum numbers. L1 and H1 have the same quantum numbers, and there is no way you can distinguish between L and H. In standard model, there is a way of distinguishing them because H is a scalar and L is a fermion. In supersymmetric theories, there is no way of distinguishing them because both of them are chiral superfields. So wherever there is a H1, you can replace it by L, and you get all the R parity violated couplings. So to distinguish them, so at the component fields, suppose depending upon the baryon and lepton number, I also distinguish the particles by their spin. Okay, by the amount of the baryon and lepton number violation, by distinguish by the spin also, then I can set these terms to 0. So essentially, that's the basic idea that if I put it on the component terms, depending upon the baryon and lepton number, okay, the spin and also the spin of this thing. So I can start avoiding these terms. Actually, what happens is, this does is also you can write it in terms, it distinguishes Higgs fields, Higgs superfields actually. From matter superfields. So it distinguishes Higgs superfields from matter superfields. That's the basic idea. Okay. And so what happens is, if you have so all the Q, U, I, D, J, C, L, I, E, J, E, I, C, all these fields will pick up a minus sign. All these superfields will pick up a minus sign under R parity. Whereas the Higgs fields just go to H1, H2. They don't pick up any minus sign. The reason why they pick up a minus sign is all of them have a non-zero lepton number or a baryon number. Okay. So all of them pick up a minus sign, whereas the Higgs fields do not have a lepton number or a baryon number. And if you change their component fields by a spin -1, essentially by a spin 2/2 of this thing, nothing changes as a component. The Higgs fields remain invariant under R parity, whereas the fields which have baryon or lepton number, they start feeling a minus sign. They start seeing the minus sign. What else changes? Theta changes to minus theta star, and all the vector superfields. Say for example, what did I call it? G mu A, W mu A, B mu A, B mu, that's it. Do not pick up any minus sign. They just remain the same. So the vector superfields don't change, whereas the theta changes sign. So that is the reason why it is called R parity, because it changes also the theta sign essentially. Okay, and the theta changes sign, and the Q's, the matter superfields changes sign, the Higgs fields invariant. Now you can see clearly. So whenever there are at least two matter fields, wherever there are two matter fields, okay, in any term, that term is R parity invariant. Say for example, here the first two terms, these two, there are two matter fields, so this remains R parity invariant, this remains R parity invariant, this remains R parity invariant. Whereas this one has three matter fields, so this is R parity violating, R parity violating, R parity violating, R parity violating. It has so odd number of matter fields will be essentially disallowed by the R parity symmetry. So odd number of matter fields or odd number of, in fact, it turns out you can actually, if you study it in terms of this super partners or in terms of the component fields, let's write down matter superfields not allowed, Lagrangian interaction terms. Also, every vertex has equal number of odd number or in other words, in other words, what happens is, so if you see this kind of, let's look at the interaction one. So the expansion of the interaction of QUH2, say for example, let's look at QUH2 and this one. So this has how many super terms? This one has 8 expansions, right? Essentially 8 expansions in terms of component fields. So it's equal couplings of UH0 and then the minus sign of it, U tilde, U. So you can take U tilde, H tilde. So this we had done last time, essentially, I think. All the expansions of this form. Okay. See, for example, this term contains U, UC, H20, U tilde, H20. So at every vertex, in terms of the component field, at every vertex, you'll have at least 2 supersymmetric partners. At every vertex, you'll have 2 supersymmetric partners. So every vertex has 2 supersymmetric partners. So in terms of super partners, in terms of the component fields, odd number of super partners at any given vertex is not allowed. Okay, odd number of matter superfields. Okay, let's put it, be more careful. Matter superfields not allowed in the interaction Lagrangian terms, and odd number of superpartners at any given vertex is not allowed. Okay. Now, given that at any given vertex you will not have any odd number of superpartners, what it means is that if you have the lightest supersymmetric partner, if there is a superpartner which is the lightest, it will not decay. Okay, it cannot decay because it doesn't have a vertex. Because there is no vertex in which there is one superpartner and two standard model particles, so there is no way it can decay. Okay, so this means superpartners can always decay only into another superparticle plus standard model particle, and thus lightest supersymmetric partner particle cannot decay. It just cannot decay. So it's stable. Okay. So the lightest supersymmetric partner is only stable. Okay. Now this is the now, like I said, the lecture marker. Okay, so all this is true. Again, I keep saying this. All this is true is only at the renormalization level. Renormalizable level in the sense that if you allow for non-renormalizable operators, okay, if you allow for non-renormalizable operators, meaning dimension 6, dimension 7, R parity violating operators are allowed. Okay, all this is true. This is the caveat. So if you allow for higher dimensional operators, say for example, non-renormalizable operators can break R parity violation. Okay. Can't break R parity. But then, so this will be, say, for example, if you write an effective field theory, effective supersymmetric effective field theory of the MSSM, so you should, if you write, you can write dimension 6 operators in terms of the fermions, component fields, which can break lepton number or baryon number or so on and so forth. So this is possible. But R parity works very well at the renormalizable level as long as you keep dimension 4 operators and dimension 3 in terms of the superpotential and dimension 2 in terms of the Kähler potential. You should be able to not have any problems with proton decay or something. Okay. So this is about R parity. Any questions on R parity? Okay. So assuming R parity, conservation not only keeps proton stable, but also keeps LSP stable, which could be one of the desirable features for dark matter. Okay, that's the reason why R parity is so popular. So R parity is so popular because it's automatically, so in most dark matter models or any other models, you need to assume an additional symmetry to keep the dark matter stable. But in this case, the moment you keep proton stable, automatically the lightest supersymmetric partner remains stable. And if luckily it's also neutral, okay, if it so happens that the lightest supersymmetric partner is neutral, you can organize your parameter space in such a way that the lightest supersymmetric partner is neutral. In such a case, then you have an automatic candidate for dark matter because that is going to be stable. Okay, that's going to be stable. So, in the present set of lectures, what we will do is essentially we will consider that R parity is conserved. Okay, we will consider R parity is conserved. We will talk about R parity violation at a later stage, essentially maybe after we finish about MS system and so on. We will talk about R parity violation maybe at some later stage, and you can ask me some details about it, and I can perhaps tell you in more details where they are useful, how the masses, say for example, for neutrinos, how they have come, what is their order of magnitude, and what is the associated phenomenology, how does the LSB decay, and what are its features, and so on, so essentially. So these are all interesting things one can study. So R parity violation is a very interesting topic. But for the present, let's just assume that R parity is conserved in the rest of the lectures because we want to have a BSM model which has dark matter and so on. So, okay. Even if R parity is violated, you can have other dark matter candidates in supersymmetric theories. Okay. So we'll talk about them later. For the present, let's just assume that R parity is conserved. So now let's talk about supersymmetric breaking. So to finish MSSM, we need to understand how supersymmetry is also broken, because MSSM tells you that for every quark, there is a super quark. Okay, and so what happens is that these super quarks should have the same mass as quarks. But that's not valid. We saw that for the example of QED, so in super QED, supersymmetric QED, we saw that you cannot have a massless fermion like for photon, okay, and the super partner of photon, and then you cannot have a scalar which is exactly like a electron, essentially, which is a electron which should have the same mass of an electron, because both of them are experimentally completely in conflict with experiments. So we need to somehow give masses to these particles, essentially. But the examples which we have seen in supersymmetric QED are essentially something called explicit supersymmetric breaking terms. We added these terms, which are soft supersymmetric breaking terms into the Lagrangian. So why don't we do spontaneous supersymmetric breaking? Why don't we do spontaneous supersymmetric breaking in the MSSM? Anybody? I think it is a well-known question, well-known answer also. So can somebody answer actually? Why don't we do spontaneous supersymmetry breaking in MSSM? Okay. Okay. What's wrong with spontaneous? Because we all like spontaneous symmetry breaking, right? We all like spontaneous symmetry breaking. Everybody likes spontaneous symmetry breaking. because spontaneous symmetry breaking. So I'm adding too many terms. Symmetry breaking always gives you soft symmetry breaking terms. Okay, always gives you soft symmetry breaking terms. That's the reason why we like spontaneous symmetry breaking. Okay, 1 second, I'll just close the door. Somebody opened it. Take the example of standard model. In the standard model, you have spontaneous symmetry breaking with the Higgs web. And what terms does it give you? It gives you mass terms for gauge bosons, matter fermions. Is there anything else it gives you? So all the terms it gives you are essentially mass terms. They're all soft. Okay, in the limit, you said V is equal to 0, you have exact symmetry again. And it, of course, it has the additional feature that it leads to renormability. So spontaneous symmetry breaking has all these features. Now, why do you want to spoil this? Why do you want to spoil this by adding explicit symmetry breaking terms? You're adding soft terms, okay? But why cannot you have spontaneous symmetry breaking already in MSSM? Like, for example, why don't you give any squark, okay? Any squark or something to any superfield essentially to get a vacuum expectation value, okay? Okay, so let's look at the possibilities. So, for example, the squarks, all the matter fields Q, U, L, E, C, okay, DC, they all have, say, for example, these have color charges. So if you give a vacuum expectation value, you're breaking QCD. Okay. So which you don't want. L and DC has electric charge. So if you break it, you're breaking QED, which you don't want. You want to conserve these two symmetries because QED and QCD are unbroken in nature. Okay. QED and QCD are unbroken in nature, and you don't want to break them. Okay. So that's the reason you don't want to give masses to, say, for example, so Q, U. So any of these quarks, or leptons, vacuum expectation values will always lead to breaking of these color charges or electric charges. Okay. Now, there is one exception. What about neutrinos? Why can't you give masses to neutrino, meaning vacuum expectation value to neutrino, and break, say, for example, not directly the neutrino field, but to the F term of the neutrino field. I'll come to that in a second. Essentially, to the F term of the neutrino field and break supersymmetry there. What stops you? It turns out supersymmetry is so interesting that you always have some condition on a given super multiplet. Say, for example, the super trace of the mass of a given multiplet always goes to 0. So that means you'll have me square, mel square plus mu el square, okay, should be equivalent to me square plus mu e square. The super trace means sum over the spins. Spin half minus sum over spin 0. Masses, essentially you take the mass squares. So you'll have relations like this. So it turns out that if you break supersymmetry, okay, these relations will still be valid. If you break supersymmetry spontaneously, these relations should still be valid. If you break it in this multiplet, say for example, if you break it in the multiplet of left-handed electrons, okay, left-handed leptons. In the left-handed leptons, you have left-handed electron, left-handed electrons neutrino. Okay, so you'll have these kind of relations. If it is spontaneously broken, if supersymmetry is spontaneously broken, you'll end up still conserving these relations. These relations still be valid. So you'll have conditions like, at least if you take neutrinos to be 0 or something, one of the electrons should be lighter than the mass of the electron. Okay, so you'll end up having phenomenologically inconsistent mass relations amongst the superpartners and standard model particles. So you'll have inconsistent relations amongst superpartners and standard model particles. Now, how do you break supersymmetry spontaneously? It turns out to break supersymmetry spontaneously, there are two ways. By giving vacuum expectation value to either F term or the D term. Now, where is it the F term come? F term comes from the chiral superfield. In the chiral superfield, you have theta theta F term. So you get a vacuum expectation values for this F term. This is equivalent to spontaneously breaking supersymmetry. This is equivalent to spontaneously breaking supersymmetry. And in the vector superfield, you have the auxiliary field theta theta bar D. So if you give a vacuum expression value for the D, you'll end up breaking again supersymmetry spontaneously. But here you have two cases: break SUSY, not gauge symmetry, but also break gauge symmetry not SUSY. So those two conditions are possible. So depending upon the choice of the parameter space and so on. So in D-type breaking, essentially. Okay, in D-type breaking, typically people assume F-type breaking. There are reasons for it. Okay, but D-type breaking, you have both the conditions that you can have either supersymmetry is broken, not the gauge symmetry, but then you can also just break the gauge symmetry, not supersymmetry in D-type breaking. That's quite a possibility. So how does this F-type breaking vacuum expectation value happen? So the F should get a vacuum expectation value. So the way you do the thing is that let's do an example of F-type breaking. Okay. So this
So
goes
one
on.
question. In this F-type and D-type breaking, does the mass relation, that super trace relation, is not valid?
It's still valid.
It's still valid, right? So
It's still valid.
we will still have a problem here.
Yeah. So unless no, within that multiplet, say for example, if the F belongs to one particular multiplet. Okay. Say for example, if you have L superfield, okay, and if I give the F type of the L superfield a vacuum expectation value, okay, then these mass relationships are still valid even if supersymmetry is spontaneously broken. Okay, did you get the point? I can always add externally extra terms, extra mass terms, but I'm not breaking supersymmetry spontaneously within the L, within any of the matter fields. Actually, that's the basic idea. So, okay, let me repeat it. Okay, if you, there are these relations which are valid as long as supersymmetry is conserved. The supertrace should always vanish as long as supersymmetry is conserved of a given multiplet. This essentially tells you that the masses are same. Okay, of a given super multiplet, the masses are same. Now, if I break spontaneously using the F of this particular multiplet, even then the supertrace still vanishes. Now there could be F's of some other place. That's the entire idea of now essentially. Now I can have F's of this particular L to be 0, say for example. Okay, but they can have additional contributions coming from outside. So supersymmetry need not be broken spontaneously within the L multiplet, not within the neutrino multiplet.
So this F term that we are giving a VEF to corresponds to some other chiral super.
Yeah, exactly. I'm come to that. I'll come into that. Yeah, exactly.
Okay.
That is called
Okay.
hidden sectors. Okay.
Okay. Thank you. Yeah.
So yeah. So L superfield F type, if I give it a non-zero vacuum expectation value, even then the super trace relations are valid, and thus we will not proceed with giving non-zero F terms, F waves or F waves for matter superfields. Okay, for all the matter superfields, this is true. So we will not proceed as. But before the okay, so what we do, I'll come to an example when an F will get a vacuum expectation value. But let's just assume that there are ways of getting vacuum expectation value. Okay. So the way you do it is assume a set of fields, set of superfields, chiral superfields, which are not charged under the standard. So under the gauge group of the standard model, they don't have any charge. So these are all singlets under the gauge group of standard model. Okay, so let me assume a bunch of phi I with representations 1, 1, 0. Okay, this I call it as hidden sector superfields. These are called hidden sector superfields. So now hidden sector, the F terms of the hidden sectors can get a wave. The F terms of the hidden sector can get a wave. Now this supersymmetry breaking is spontaneously broken. So Suzy spontaneously broken in hidden sector. Okay, so you break supersymmetry spontaneously in the hidden sector. But then, so there is a hidden sector here. And this is the MSSM. MSSM, all Fi of MSSM are equal to 0 because of the condition we just said. Okay, all the F terms of the MSSM are set to 0. So they don't break supersymmetry spontaneously. But here, Fi not equal to 0. This is communicated to the MSSM by some methodology by a sector called messenger sector. Okay, this messenger sector is not something very different essentially. This messenger sector could be, so messenger sectors could be gravitational interactions. It could also be gauge interactions. Okay, so in either case, whether it is gravitational interactions or gauge interactions, you will end up having an L soft here, which is soft supersymmetry breaking terms. Okay, so in either case, you'll end up having an additional soft terms. These are how you generate your soft terms. Okay, so even if you forget about this entire sector, okay, even if you forget about this entire sector, you can work with MSSM because all the effect of this entire sector is essentially to give you an L soft. Okay, this entire physics essentially gives you an L soft essentially. Okay, now what is L soft? I can then I'll go into the details about these things both in terms of gravity and gauge interactions a little bit a bit later, but let's just see what is L soft. We already have a clue what is L soft actually. We already have what is L soft. And let me just stop here. You have any questions here essentially? If anybody has questions, then I can elaborate on it right now. I can Okay, yeah. So what is LSOFT? LSOFT is a set of terms, soft supersymmetry breaking terms, similar to what we have seen for QED. Okay, very similar to what we have seen for QED. Set of soft supersymmetry breaking terms, which are essentially parameterized, which break supersymmetry, which containing one. So what should they contain? Mass terms for super partners. Essentially, what they should contain mass terms for super partners. So mass terms for scalar super partners. So what would be the mass terms be? So m square ij, okay, qi, dagger qi, m square ij di, the dj, m square ij ui c, dagger ujc, plus m square ij li dagger lj, m square ij ei tilde star ej. Now notice that I put I and j separately. It is not just for the first generation, second generation, third generation. I can have 1, 2 also, 1, 2, 1, 3 terms also. That means they can violate flavor. That means they can be intergenerational. Why I'm allowing it containing? Because all allowed terms which satisfy GSM. So this term is invariant under standard model gauge group. And even if I put I not equal to j, it is still invariant under standard model gauge group, because the gauge group does not distinguish between first generation and second generation. Okay, the gauge transformations are the same, whether you are first generation, second generation, or third generation. The only thing which distinguishes generations is the mass terms, which are essentially coming from the Ikawa couplings. But when you are breaking supersymmetry, you automatically break the intergenerational what do you call distinction, and so you're breaking meaning your flavor symmetry is broken. So supersymmetry breaking terms, the mass terms break flavor. In the QED case also, we didn't care about flavor because we only had one electron and one selectron. So we didn't care about generations essentially. If you put in a QED with electron and a muon, say for example, then you'll also have the same problem in QED also. Okay, in QED also you'll have the same problem essentially. The moment you put in electron, we wrote down those terms which break all possible supersymmetry breaking terms. Then scalar superpartners, then the Higgs mx square h1 dagger h1 h1 square mh2 square h2 dagger h2. So all the scalars get masses, and then mass terms for gauge superpartners. So essentially, which means for gauge nodes. So you have m gluino g mu a tilde G mu A. 8 gluinos get the same mass on an octet, M gluino, M vino. All the 3 vinos get the same mass. And then vino. Okay, so these are the gluino mass, vino, vino. So these are the mass terms which also break supersymmetry. Okay, and correspondingly, vino has a mass which is MW, vino has a mass which is 0, gluino has a mass which is 0, a gluon has a mass which is 0, photon has a mass which is 0, and W and Z have roughly 90 GeV, 80 GeV, and 90 GeV. The third ones are the trilinear couplings. So in the QED case, if you remember, we had only one term in the superpotential, Me phi phi. So we wrote down one term, Be scalar phi E, scalar phi E, in the soft supersymmetry breaking terms. So similarly, but here you have trilinear couplings because you have the entire Yukawa coupling, Yukawa potential in your superpotential. Okay. So this is your superpotential. So for every term in the superpotential, you can write the scalar counterpart. For every term in the superpotential, you can write the scalar counterpart. So those are your trilinear couplings. So this is Aijk, okay, Qi, Auijk, Qi, UJC, H2. This is also tilde. These two are tildes. This is a scalar. Okay, this is a scalar. H2 is a scalar. All three are scalars essentially. There is no star. Then ADIJK, QI tilde, DJ tilde, H2, H1, AEIJK, LI tilde, EJCK, H1. Okay. And then you can also add bilinear couplings. Bilinear couplings are B mu H1 H2 plus X. So the dimension of A terms is dimension 1 because these three are scalars. H2 is a scalar, H1 is a scalar, mu tilde and everything. So A is dimension 1. So typically it need not be always the case, but for easy, what you do is AUIJK, you parameterize as AUIJK dimension 1 times YUIJK. So you parameterize it by mapping it with Yukawa coupling. Essentially, that it's mapping it, factorizing the Yukawa part of it. Essentially, you say it is some scalar constant factor times Yukawa coupling. So you can always write, because it's a free parameter, AUIJK is free parameter. So, but if you write it in terms of the Yukawa coupling, so then you can keep, you have much more control, meaning in the sense that you can keep track of all the, where is the flavor violation coming in, where is the Yukawa couplings coming in, where is the new source. It becomes, life becomes much, much easier the moment you factorize in terms of the Yukawa coupling, essentially. That's precisely the reason why all the trilinear couplings, you write it down in terms of some factor times the Yukawa coupling, essentially. So factorize it that way, life becomes easier because then you can keep track of everything. I mean, so you can keep track of what is the source of flavor violation coming from supersymmetric theories, and so on. So these are all your bunch of soft supersymmetric breaking terms. Now you can count them. Are there any terms which I am missing? Okay. Now, if you count them, you can count them. They're extremely large number, essentially. They are about 100 parameters. It turns out they are really 100 parameters. So a large number of parameters. Which are also violet, flavor, and C. In addition to supersymmetry. So they not only break supersymmetry, but also break flavor and CP. Okay. So you have new sources of flavor and you have new sources of CP violations. So what we call MSSM today is again L gauge, L MSSM is equal to L gauge, L kinetic, essentially, which is coming from the Kira potential, and then L Yukawa, which is coming from the W, and then there is L scalar, which is nothing but F square plus D square, and finally you have L supersymmetric breaking terms. L supersymmetric breaking terms. Okay. Also, you also have this L curly W kinetic terms for the gauge bosons and the gauge inos, which is coming from the gauge kinetic function. Okay. So this entire thing is now what we call as the MSSM. This is the MSSM, okay, which has a full Lagrangian given in this particular format. Okay, adding all these terms. So now you see that this Lagrangian is huge, just all these terms. This is the so-called MSSM. But this MSSM, you break supersymmetry, but you have not yet broken, or you have not yet you didn't break at this the Higgs or the standard model gauge symmetry. This is still intact. Okay, this is still intact. Still conserves SU2 cross U1 Y times SU3 color. So you need to break. Okay, you need to break this symmetry. So you need to incorporate. Okay, you need to incorporate the SU2 cross U1 breaking into this particular thing. Okay.
So here this LSSB contains all the soft terms.
LSSB contains all the soft terms,
Okay.
all these 100 and all these mass parameters. And
okay.
Okay. Okay. Any questions on MSSM? Okay, if instead of SSB, let me call it a soft if you want. L soft. makes it easier. I think I wrote it as L soft or what? Okay. I wrote it as L soft. So let me just write it as L soft. So LSoft has its origins because all these terms are these origins coming from hidden sector. So you are breaking explicitly supersymmetry in MSSM. You are not breaking spontaneously within MSSM. Supersymmetry is spontaneously broken somewhere else, somewhere we don't know where. Okay, it's broken in some gauge sector, essentially a gauge singlet sector. Somewhere else need not be physically somewhere else. It could be meaning in the same space-time point, but these fields are not charged under the standard model gauge group. Okay, these are fields which are not charged in the standard model gauge group. They are broken. They don't have standard model gauge groups. So supersymmetry is spontaneously broken there, and then it's communicated to MS system either by gravitational interactions or gauge interactions. We'll see these examples. Okay, and then it leads to any of these cases, however it's communicated, it could be in a number of ways. The most general form of LSoft we have already determined and we wrote it down, and together this gives you the MSSM. This entire thing gives you the MSSM. Okay, so now let's do how to break. Still this MSSM is not complete because we have not incorporated electroweak symmetry breaking. Okay, we have not incorporated electroweak symmetry breaking. Okay, so let's do that essentially. So we want to do electroweak symmetry breaking. Any questions before I proceed to electroweak symmetry breaking? Okay, good. Okay, so we want to incorporate electroweak symmetry breaking as close to standard model as possible. So we want to do it in the same manner as well. So what we want, the Higgs fields should get vacuum expectation value. And lead to electroweak symmetry. That's the basic idea. So in that you want, but instead of one single Higgs field, you get two Higgs fields, which give you a vacuum expectation value. That's the only thing which you do. Okay, so for this, we look at the Higgs potential. Of the analysis. So the Higgs potential you want to see from the MSSM. So first is the F terms. F terms essentially coming from del W by del H1 whole square. So that gives me mu square H2 square. Similarly, you'll have mu square H1 square. Then D terms. The D terms are the general forms is G square phi I star tau A phi I. Like this we said it earlier. So this gives me G square plus G prime square, because both of them have, gives me H2 0 square minus H1 0 square whole square. Okay, so this is dA. dA is this. So the D term 1 by 4 should be there. 1 by 4. So 1 by 4, this 1 by 2 dA. This is the term. Okay. Each dA is equal to G times phi I star tau A, the generator for phi A. So tau A is 1 by 2 for SU2. So this you can guess it, because how do you get the G terms for this thing? T3 value is tau A is essentially the T3 value for the Higgs representations. So the two Higgs representations are H2 plus, H2 0, and this is H2 0, H1 0, H1 minus. This has a T3 value half. This has a T3 value minus half. So you have a half here. So overall there is a half factor. So that gives me 1 by 4. Okay. So G square 1 by half square. So this gives me H2 0 square, and minus half square gives me minus. So there is a little minus sign between the H2 and H1 0. So that gives me this entire minus sign. I hope I have done the correct assignments for H2 and H1 0. I don't know what I did last time. But independent of that, there you see that there is a relative minus sign. Okay, H2 is half. Okay, H2, H1 0, H1 minus. Okay, hey, correct. Okay, minus half. T3 value is correct. The hypercharge is minus half. Right. Okay, good. The hypercharge is minus half plus half. So for G prime also there will be a relative minus sign, and for G T3 value also there is a relative minus. T3 also there is a relative minus sign, and for G prime is Y. Y is minus half, and Y is plus half for here. T3 is this. Okay, T3 is this. So you see that there is a relative minus sign. So you'll end up having this kind of a relation. So these are your supersymmetric conserving terms. So these are your supersymmetric conserving terms, which is F square plus D square, essentially F square plus D square. Now D square essentially is, yeah, is a quartic term. So this is the only possible quartic term you'll have in the entire supersymmetric terms. Okay, so L Higgs is equal to L F square L F square plus D square plus L soft. Only for the Higgs neutral, H1 0, H2 0. Here also H1 0, H2 0. You don't write all the soft terms for all the Higgs components, not for the charged Higgs component. You're only writing for the neutral components of the Higgs, because only the neutral component should get a vacuum expectation value. So this gives me, so LF square, so this LF square, L soft contains, so L soft, let's write down, L soft contains MH1 square, H1 square, plus MH2 square, H2 square, then minus B mu, H1 0, H2 0. That's it. Let's see. So I have the D square term, I have the F square terms. So with this, I can write L Higgs. Okay, I can write the L Higgs. So L Higgs is equal to MH1 square plus mu square mod H1 square plus MH2 square plus mu square mod H2 square. These are all zero components, by the way, neutral components, minus B mu H1 0 H20 plus Hc plus 1 by 8 G square plus G prime square H20 square minus H10 square whole square. So this is 1 by 4. Actually, there is a 1 by 2 factor coming because 1 by 2 whole square is 4 or 1 by 8 actually. Okay, that's right. It should be 1 by 8. 1 by 8. So there is a 1 by 2 here. The square of T3, square of y should give me 1 by 4, 1 by 4, 1 by 2, that's 1 by 8. So that gives me 1 by 8 G square plus G prime square, V2 square minus. So now to make life easier, I will just set H20 is equal to V2, H10 is equal to V1, V2 by V1 is equal to tan beta, and V2 square plus V1 square is equal to V square. So V2 square plus V1 square is equal to V square because V square should correspond to standard model V square. So this is the condition we had to put because we need to get back the standard model essentially. We need to get back the standard model like relations. Even if we have two Higgs doublet model, their breaking should give me back a vacuum expectation value, which should be equivalent to the sum of them should give me back your standard model essentially. So your mz square mass should be 1 by 4 g square plus g prime square v square. And mw square mass should be equivalent to 1 by 4 g square v square. So these relationships should be valid. Okay, this is your Sm. So this Sm should be equivalent to your v square essentially. So Sm should be identically equivalent to your vs. Okay, v square. So you should get back your standard model relationships. So that's the reason why you put these conditions. Now, seeing this potential, you have a quadratic terms in the field, and then there is a quadratic term which is not radial part, which is H10, H20. So this is not radial. There is no cubic term, but there is a quartic term. So there is a quartic term which is just determined by the gauge index. This you see that this, if you want, I can take this is as mz square. This I can write it as half mz square cos 2 beta, cos square 2 beta, cos square 2 beta, because this is nothing but half mz square cos square 2 half. Maybe the half also cos square beta minus sin square beta. That's called sin cos square beta minus sin square. That's cos 2 beta, cos square 2 beta. Okay, and this is just 1 by 2 mz square v square. Okay, so this is just mz square cos 2 beta, because the moment I substitute everything here, this is nothing. V2 is equal to, this means V2 is equal to V sin beta. Yeah, and V1 is equal to V cos beta. Okay, so now you have conditions that this is negative. So this is negative. So this should not pull this quadratic part. So if you want to plot it, this should not pull it so much negative so that you lose the positivity. So this goes, so in the, okay. So this gives me conditions that bounded from below. So you have this condition that 2b mu should be less than 2 mu square plus mh2 square plus mh1 square. This is obvious because if this becomes larger than these two terms, okay, if this becomes larger than these two terms, okay, the potential is no longer bounded from below, you won't have a vacuum expectation value. Okay, so you also have need to, okay, maybe I should put a v by root 2 here, sorry. I didn't. Okay, you also need, but at the end, you should have, oh, at least one of the Higgs mass squared should be negative, so that it gets a web. So that means if you take the determinant of the Higgs mass matrix, now you can write a mass matrix for the neutral components. So these two are the diagonal terms, and this is the off diagonal term. So these two are your diagonal terms in H1, H2 space, and this is the half diagonal term, and the determinant should be negative. So the determinant should be negative gives you a condition. That means one of the eigenvalue of the Higgs mass matrix should be negative. So B mu square should be greater than, of course, mod mu square plus mh2 square product mu square plus mh1 square. So that means you're making sure if you write the Higgs mass matrix h1 0, h2 0, so you have m1 square, mh1 square plus mu square, mh1 2 square plus mu square. This is your b mu. Okay. So what you're asking is essentially the determinant should be at least negative. So this is the determinant, b mu minus b mu square. So the determinant should be negative, means that this should be at least greater than these two, product of these two. That's essentially what you wrote down here. Okay, that essentially it should be this, at least one eigenvalue should be negative. So this in the standard model, this is equivalent to saying that mh square should be negative, right? Essentially, mh square should be negative, not h2 square, sorry, supersymmetry. So, or mu square in the standard model should be negative. We put the condition mu square sm should be negative. So that's equivalent to this condition essentially. Okay. So with this, you have made sure that your potential is bounded from below. So in the standard model, you have to ensure that lambda is greater than 0. In the supersymmetric standard model, you don't have to ensure lambda is greater than 0 because it's always goes as the gauge coupling square. It always goes as gauge coupling square. So it is always positive essentially. It's always positive. So the lambda, we in the standard model, you have mu square negative and lambda greater than 0 condition. So that is lambda greater than 0 is always satisfied here in the sense that you end up having because the quartic coupling is essentially the Higgs coupling, essentially it's the gauge coupling. So one last, so with these two conditions, I can derive two important relations. No, this is correct actually, v2 square plus v1 square. Okay. These two these are called the minimization conditions. And this ensure the electroweak symmetry is always broken. So this is half mz square is equal to mh1 square minus tan square beta mh2 square minus tan square beta minus 1 minus mu square. The second condition is sin 2 beta is equal to 2 b mu or 2 b mu mh1 square mh2 square plus 2 mu square. As long as these two conditions are satisfied, your electroweak symmetry breaking is always valid. So electroweak symmetry breaking is happens. Now this is a very interesting equation. It's a very interesting equation. Now this equation relates to completely distinct parameter sets to each other. Like for example, the soft. So these terms are your soft terms. It relates your soft terms to a physically measured soft parameter, which is mz square, and then this is a supersymmetry conserving parameter mu square. So your soft terms, which are supersymmetric breaking terms, are related to supersymmetry breaking parameter and then a standard model measured parameter. A standard model measured parameter mz square is very highly precisely measured. So these are tree level relations. These are tree level relationships. So they're subject to radiative corrections. So there could be some small. There should be any radiative corrections to this should be small. Otherwise, because these are highly well measured, otherwise they could lead to fine tuning, as we'll see later on. The second equation essentially fixes your tan beta. Your tan beta is related always. You can always trade your one of the soft terms into your tan beta definition using this relation. So you can at least trade one of the parameters of the Higgs potential, at least two of the parameters of the Higgs potential. Okay, you can reduce the number of parameters in your Higgs potential by using these minimization conditions, because you can trade tan beta, and then in principle you can also trade mu square, because your mu square is supersymmetric conserving parameter is now determined in terms of supersymmetry breaking terms and the soft supersymmetry. And the mz square mass. So to completely unrelated sectors, because soft supersymmetry breaking terms are coming from some hidden sector related physics. Okay, they are coming from completely unrelated sector, and supersymmetry conserving term is coming from MSSM. It's completely determined by the MSSM gauge symmetry. It has no knowledge about how supersymmetry is broken. It doesn't care about it. These two get related by these particular relationships. Okay, and mz square essentially, of course, is your precision high energy physics parameter. Okay, so mz square is the mass of the size. So second one is a tan beta. Tan beta is the ratio of the vacuum expectation values, how supersymmetry is, how standard model gauge symmetry is broken, whether it's broken dominantly into one of the Higgses or equally into both the Higgses. When tan beta is equal to 1, it's broken equally in both the Higgses, or it's broken dominantly in one of the Higgses. That tells you that's what the tan beta tells you. Okay, that can be related to a soft supersymmetry breaking term, which is the bilinear term. Okay, times some soft terms with these relations. So you can trade two of the parameters, either mu square and both mu square and b mu, to tan beta and Okay, you can determine completely tan beta and mu square by these relationships, by any choice of these relationships. That way, you are in the parameter space which satisfies your electroweak symmetry. Again, I repeat it that these relationships, these minimization conditions are very essential, but they can be subjected to radiative corrections. So the radiative corrections can be very, very large, and they can play a big role as such. They can be subject to it. Okay, so these two conditions should be always be valid by any, when you are choosing any supersymmetric parameter space. You make sure that your minimization conditions are always valid, whether it's PMSSM or you don't care about meaning. Because if these two conditions are not valid, your electroweak symmetry breaking is not valid. So whether you're choosing minimal supergravity, gauge mediation, or any other model, these two conditions, or PMSSM, just random scanning essentially, PMSSM, these two conditions should always be valid. These two conditions should always be. Okay. Okay, so that your electroweak symmetry is good. So the next, any questions on this?
So, so this definition of tan beta, is it always the ratio of the Higgs that gives mass to the down type divided by the up type? Or the
Here I did the up type divided by the down type. V2 by V1.
but V2 is giving mass to down type in our
In our notation? Okay.
yes, because
Oh, is that so? I thought, okay, I typically use the other way around. Maybe I may be
because
wrong actually.
H2,
No, but this is your choice.
okay.
This is V2 is given to uptype. Okay.
Yeah. Okay.
Okay. So tan beta is V2 by V1, but that is typically the notation, but it's your choice. It's your choice. Okay, where is the tan beta? Here. I chose this one. This
V2
is
by
is typically the popular one. But
up type divided by down type.
up type divided by down type is the popular one.
Okay.
So that because the top quark has a very large mass. Okay. So the large tan beta. Oh no. Oh no. Oh no. 1 second. No, it should be down type by up type. Okay. Let me see if I have written something on my notes potentially. What did I choose? All right. Okay. So now, right, you're right. Essentially, large tangent beta happens when V1 is very, very small. But large tangent beta, okay. 1 second. See, in the limit of large tangent beta, typically the notation is that the down type becomes very, very large. The Cow couplings of the down type becomes large. So in the limit of large tangent beta, what happens is, let me see. Large tangent beta, so cos beta is equal to sine beta. 1 second. Tan beta time sine cos. Yeah, that's correct, I think. So what happens is sine beta becomes 1 in the limit of large tangent beta, whereas cos beta becomes larger, right? Cos beta is equal to 1 by 1 plus tan square beta. Okay, tan square beta is equal to 1 by tan beta smaller. So plus by tan beta. What is it? I forgot my trigonometry. One second. Right. So sin beta becomes 1 in the limit of large tangent beta. I think I'm correct. It's 1 cos beta versus 1 by tan beta. Okay. So the Ika couplings of the Ika couplings, right. Ika couplings YE becomes ME by V1, right? That's right. You're right. So V1 goes as 1 by tan beta. So that is increases by tan beta. YE and YD MD by V1 up to a factors root 2, okay? MD by tan beta. So this is right. This correct. This is correct. So in the limit of large tangent beta, the Ika couplings YE and YD increase by tan beta. Okay. So that is typical notation that large tangent beta requires the down type Ika couplings to increase. Okay. Do you agree with this?
Yes.
Yeah. Okay. Yeah. So the down type Ikawas should increase with large tangent beta. That's typically the thing. But this is, of course, if you look at some old papers, you find both the notations. Meaning, there are notations with V1 by V2 also. There are some old papers with V1 by V2. But over the when this large tangent beta effects were discovered, this notation was sort of finalized. That you choose V2 by V1, and so you can have the effects of large Ika couplings in the down type sector due to the presence of large tangent. So in fact, you can have a region with very large tangent beta where top, bottom, tau, all the three Ikas unify. Okay, all the three Ika couplings can unify, so they all have the same values. Okay. For example, Anant has worked out those things. He became famous because of those things, essentially because he could predict from the unification of this top, bottom, and tau, he could predict the top mass. Okay, he just by assuming that unification, okay, he could predict the top mass.
So with increasing tan beta, since this top Yukawa will decrease and this
top Ikas will not increase because sin beta becomes 1.
Yeah, it will decrease. Up type will
It will
decrease.
decrease very little. Uptype will decrease very little. It becomes stagnant if you want.
Okay, okay.
It becomes constant. It won't change
Down
significantly.
type will keep on increasing.
Yeah, YE and YD will keep on increasing unless they until they reach the non-perturbative limit around 60 or something, tan beta 60 or something. They reach the tan beta non-perturbative limit, and they start blowing up. There are other issues actually. Okay, they start blowing up, and you have tan beta, meaning top bottom tau Yukawa hitting up 4 pi and so on. Okay. Okay. So we'll stick to this notation. I think this notation is correct. Okay. So we'll stick to this notation, and then we'll study in the next class. So given this particular electroweak symmetry breaking, what is the spectrum, final spectrum you get essentially of the supersymmetric partners? So what is the final spectrum you get of the supersymmetric partners? Okay. Okay. So maybe I'll stop here. Any questions? Okay. So the next class, you guys are back, right? So Tuesday, next Tuesday, you'll be back. We can have an offline class, or we should be have online.
I'll be back on 11th, right?
Yeah, I think so. It's 11th, right?
Yes.
Yeah. Okay, just let me know. For me, it doesn't make a difference whether it's offline or online. So if you just let me know, I can, either way is fine. Okay. By popular choice, we can either do online or offline. Okay. All right. Okay. Okay then. So we'll meet in the next class, and where we'll look at the spectrum, the MSSL spectrum, all the soft terms, and after electroweak symmetry breaking, how does the spectrum change? Okay, that's what we'll look at. Okay. Okay.